Hi, I'm Steve Ward, and in this session we're going to look at the fundamentals of power supplies for PLC applications. So PLCs are used mainly in industrial applications, so they need an industrial power supply. So in industrial control, the power supply, or PSU, is used to convert high mains voltages into the lower level voltages used by typical industrial devices, including PLCs. And in the European Union, there's a machinery directive which specifically mandates the use of low safe voltages. Typically anything higher than 40 volts gives you an electric shock risk, and higher voltages can even be fatal. So we often prefer to use 24 volts because 24 volts gives us a high degree of safety, but still providing enough current to have some noise immunity and also the current capacity to drive more powerful devices. Now, having said that, the incoming supply often isn't 24 volts DC. It would normally be a mains voltage, maybe 110 or 230 volts AC. So we do need the power supply to convert those incoming main voltages into those low voltages. So to do that, we use an industrial power supply, which is a modular, rugged unit designed to cope with wide temperature ranges and harsh environments. That may include anything from a simple metal enclosure. It might give you some protection against being able to touch the voltages, but it might go up to including ATEX or IEC EX certification, and it may even include marine approvals as well as other industry specific approvals. Now, with a simple system, you may use a single power supply, but the downside of this is single power supplies may not provide enough power, but you also might get noise coming between the different wiring systems, and it might be that, for example, outputs might interfere with inputs and might even interfere with the system because you can get noise transmitted on the power rails. So larger systems typically use multiple power supplies to achieve the desired power levels and also to segregate different types of power. In redundant systems, we also need to use multiple power supplies to cover possible failures. So for example, you might have two power supplies in parallel, and if either power supply fails, the other one can take over. And I'm not going to talk about this too much, but we also might have an interruptible power supply, or UPS. This can be used to ensure power delivery in the event of a mains power supply failure. And that's a device that consists of power converters and batteries. And the idea is we take the mains voltage, convert it into DC and charge up batteries. And then if the mains input fails, we take the output from the batteries and convert them into AC, or possibly keep them as DC. And they are used to provide power to the control system until the AC mains recovers. So let's look at how to wire power supplies to the PLC and to the I/O devices. The easiest arrangement is a single power supply, which is appropriate for a simple small system. So there will be one power supply, and what we have there is we have the incoming AC supply on the left hand side. That goes through the power supply and it's converted into the lower level DC voltage that we use for the actual system itself, typically 24 volt DC. So we would use that same voltage to provide power to all the components. So there will be the operator interface, if there is one. There would be the PLC CPU. There would be the I/O power to the actual I/O modules themselves because they need a power supply. There would be the wiring to the input devices, and then there would be the wiring to the output devices through the output modules. So the actual physical wiring might be quite complex, but the overall idea is quite straightforward. So this is fine for where you have small currents. Typically, you might use maybe a 5 amp power supply or a 10 amp power supply, and that can be more than enough to power all of these components together. But as the systems get larger, you typically run out of power on the output side, but you may also run out of power on the input side and also for the other devices that you're trying to control. Now you can get bigger power supplies than 10 amps, 20 amps is possible, maybe even 40 amps. Obviously at this stage the power supply would be getting quite bigger and bulkier. You could even wire potentially multiple power supplies in parallel to get even more power. But the biggest issue, it's more about the noise and the segregation more than the actual size of the power supply itself. But anyway, for a simple system, for a small system where the power supply requirements aren't too demanding, a single power supply can be adequate. It's common though to separate the power supplies even in simplex systems. and my preference would be at least 2 power supplies. So we'd have one power supply for the system, so that would provide, for example, the operator interface and the PLC CPU, and then we'd have a separate supply for the I/O. So there'll be a separate power supply which provides power to the I/O modules and the input devices and the output devices. 2 key reasons for doing this. One, of course, we get more power without having to go to really big bulky power supplies. You could use 2 5 amp or maybe a 5 amp to 10 amp power supply or so on. Another big reason is it reduces the noise on the system side. Operator interfaces and PLC CPUs are relatively rugged, but if you expose them to too much noise, particularly from output devices which aren't adequately suppressed, you could be running the risk of getting a lot of noise on the system, and that could affect the operation of the operator interface on the PLC CPU. So simply having 2 power supplies like this is a great way of segregating the power and making it quite straightforward and making sure that there's minimal interference across the 2 systems. It might be necessary to connect the 2 0 volts together. That would depend on what the isolation of the different devices is. That may or may not be required. There would also be a requirement for earthing, but I'll come on to that later. Now, there's still a possibility of interference from the outputs to the inputs. That's less of an issue if you've got mostly discrete I/O all running at 24 volts DC, but it is common to see crosstalk and interference coming from DC outputs going into analog inputs. So if you ask for very high analog accuracy, then you may prefer to isolate the input and the output supply. So now we're up to 3 power supplies. We've got at least 3. There will be one for the system, there will be one for the inputs, and there will be a set one for the outputs. And if you're really concerned about the analog system, you may even have an additional power supply or power supplies to provide the analog devices, because that makes extra sure that you're having isolation between the inputs and the outputs and both discrete and analogs. If you're doing that, you'd also need to look at the wiring, because you'd need to make sure the analog wiring is maybe segregated from any discrete wiring, certainly from any high power wiring, and you may also look at shielding and earthing in more detail as well. But the key point of doing this is it reduces noise on the system side and from the inputs and the outputs. Definitely recommended where you have outputs which are highly inductive, such as a lot of contactors and solenoids. So more power supplies, not too much more complexity. Again, you might want to tie the 0 volts together, or you might be relying just on the earthing and protection you have from the isolation of each device. So some of this is going to be application dependent, but this isn't going to cost too much more, and it's not going to complicate your wiring too much more, but it does give you quite a lot of benefits in terms of segregation for noise, as well as possibly reducing the overall size of each individual power supply, even if you need more of them in total. Redundant systems often need more power supplies, and typically it's the power supply in the system that's the least reliable part, although that's arguable. So what you typically need in the redundant system is at least 2 power supplies, one in case of failure of the other power supply. They can back each other up. But again, to be able to separate the I/O system from the system supply, then you probably need even more power supplies. I'd recommend a minimum of at least 4 power supplies. But again, as before, you might have additional power supplies to separate inputs and outputs. Now for the system supply, if you've got 2 separate controllers, they can just have 1 power supply each. So you'd have your master system supply, so a master power supply which controls the master PLC, and then you'd have a backup system supply and the backup power supply controlling the backup PLC. And in the case of any single point of failure, there you're covered, because the other system will take over if the first one fails. For the I/O system though, the I/O system is often not redundant. You're often using a Simplex I/O solution, but you still want a redundant power supply. So the way we do this now is we still have 2 power supplies, but now we have an additional redundancy module. And what the redundancy module does is it takes in the 2 power supply inputs, and then it provides adequate power supply to the I/O modules from those 2 sources. So we'd need to supply a power supply which is capable of driving all the I/O. So for example, that might be 10 amps. in which case we'd need two 10 amp power supplies. The redundancy module then would need to have a current capacity which matches the power supply in order to be able to supply that same amount of power to the I/O modules. And effectively what's inside that redundancy module is a set of diodes, or maybe MOSFET technology, but what it's doing is it's isolating the two power supplies but allowing whichever power supply is dominant to provide power to the I/O. But if any one of those power supplies fails, then it allows the other power supply to take that power and supply it to the I/O instead. So we need more power supplies, typically four, two for the system and two for the I/O system supply. And then we also need that additional redundancy module as well. So now we're up to at least 5 components, but you might also want additional components again to segregate inputs and outputs, and maybe even more if you want to segregate analogs and discretes, as we said before. Now, it might not be necessary to use a redundancy module. The reason for using the redundancy module is it allows us to have a power supply arrangement where you've got two power supplies operating in parallel. So you need minimum 2, and this would be ideal for power supplies which do support parallel operation. So typically what we have here is we have the two AC supplies coming in, that's split out to the two power supplies, and then they are just combined together on the output side and go directly to the PLC and the I/O. You need to make sure that your power supply is designed for parallel support though. Otherwise what could happen is, if you've got one power supply that's producing a slightly higher voltage, which is quite likely, it's very unlikely you'll get two power supplies providing exactly the same voltage. If they're providing slightly different voltages, what could happen is you could end up sinking power from one power supply into the other one, and that could cause overheating or damage to one of those power supplies. So typically the way that parallel operation is done is with diodes on the output. So quite simple arrangement from an electrical point of view, but it needs to be built into that power supply. Now, if the power supplies don't support parallel operation, then you can add those diodes externally. And it's a very simple circuit. It's just a forward bias diode from the positive output of each power supply, and then they're wired together to the same positive to the actual PLC or I/O. So again, simple supply arrangement, single supply coming into two power supplies paralleled up, but with that additional diode on the output of the power supplies. So that's an arrangement for when power supplies do not support that parallel operation. Now, some power supplies have that diode built in, so you don't need that. The other option is, as I said, to use that redundant supply arrangement where we use that redundancy module. And this is what's inside that redundancy module. Effectively, the redundancy module contains those two diodes. And the reason you use a redundancy module rather than just wiring discrete diodes is those diodes might need to be quite big. We're not talking about a simple 1 amp diode here. Often that's 10 amps or 20 amps or 40 amps. So it's quite a beefy diode. So that's why you might use a redundancy module rather than try and just configure this with two simple diodes using a simple terminal. There's another aspect here, which is inside that redundancy module. If you use diodes, there's a volt drop across the diode. So typically with a silicon diode, there's a 0.7 volt drop, which might not be relevant, might not be an issue. But if you've got a 24 volt power supply, you're now running at 23.3 volts because of a 0.7 volt drop. And if there are further volt drops due to terminations and so on, that means that your final voltage at your device could be lower than you really need it to be. So for example, if you consider the PLC output, which might also have a diode inside, you might have resistance at the terminations which reduces the voltage. So you might start with 24 volts at the power supply, but you might be down to 20 volts or even lower at the actual physical output, and that might not be enough voltage or power to actually control the output. So one thing we can do with these redundancy modules is we can use MOSFETs instead of diodes, and a MOSFET, it's still an electronic device, but it has a much smaller volt drop. That can also affect the heat dissipation as well, because where there's a volt drop, you're dissipating power, which causes heat. So it can be useful to have a MOSFET which has a lower volt drop, and that implies less heat generation as well. So that can make your panel arrangement simpler, and it means you're wasting less power. So this is effectively what the arrangement looks like using these external diodes. But as I say, using a redundancy module can help because that can give you better electronic arrangements and also make it easier to wire as well, rather than have to individually wire to discrete terminals. Let's take a look at calculating the power required for an application. So power supplies come in a range of different sizes. Typically a small power supply might be 5 amps, a common size might be 10 or 20 amps. You can get bigger supplies as well. So how do we calculate how much power is required? So typically what we do is we take the power requirement for each component in the system and we add up all those DC power requirements. So if you've got a CPU that takes 1 amp and you've got an operator interface that takes 1 amp, and then maybe you've got some IO modules which total at 1 amp, that's 3 amps in total. So 3 amps times 24, that gives you about whatever it is in terms of wattages. So say 48 watts if it was 2 amps. So then you would choose a 48 watt power supply. Or if you just have a power supply that's calculated in amps, then of course you could just use a power supply that had a 3 amp output for that scenario. If you're not having power available, then it might also be possible to multiply the voltage and current as we just did, or sometimes you might be able to work directly in amps as we just did as well. It's important to add a safety or expansion margin, and typically this could be anything from 20 to 50%. You don't want to over specify too much, because having too big a power supply costs more and also means that you're running the power supply in an area where it reduces efficiency. But you'd certainly need some sort of safety margin, and possibly if you're going to be expanding in future. So if I needed a 3 amp power supply, I would probably round up to 4 amps or maybe even 5 amps. You might also need to consider inrush current as well. So you might need to look at how much overload capacity your power supply has, because it's common for electronic devices to need 2 times or sometimes even more of that current or power when they first start up. So it might be that your 3 amp system actually takes maybe 4 or 5 amps to power up, in which case that's where you need your 5 amp power supply, unless the power supply was capable of driving more current. Now in an AC system, you then take your DC power along with the power supply efficiency, and that will derive your consumed power. Typical power supply efficiency is 80 to 90%, but if you're not sure, you should assume a lower efficiency, maybe 75%. So on our incoming power, you typically take your power supply. So if we've got, say, a 5 amp load, 5 times 24, that gives us about 100 watts. It's actually 96 watts, but 100 watts is close enough. You don't have to be 100% precise on these things. So we've got a 100 watt power supply. If we assume 90% efficiency, then that means the incoming current, we take that DC or current, divide it by 0.9, and that would give us actually an AC input of 111 watts. And then we probably need to add a bit of safety margin on that as well. AC power is less important, but it can be useful if whoever's supplying the power wants to know how much power you're going to be consuming. So that's how we calculate the AC input power. And of course, you'll also need that to check fuses and so on. So once you know you've got 110 or 111 watts on the incoming supply, you could then translate that into voltage. So if it was a 110 volt supply, that would be a 1 amp fuse. If it was a 230 volt supply, then it would be about a half amp fuse. And also to take into account the inrush, you might use a miniature circuit breaker, or if it was a fuse, you might choose a slow blow fuse, because there might be an inrush current on that as well. So variety of different ways we can calculate power, but basically it's by understanding the individual power consumption of each device, either as power or current, and then adding all of that up together until we get the final power, and then multiplying by the power supply efficiency to get the actual AC input power. A lot of people also want to know what heat dissipation is. Interestingly, heat dissipation is generally the same as the power consumption, since most of the energy that's consumed by the electronic components is emitted as heat. A very small amount might be emitted as light from LEDs. So for example, if you've got a typical red LED, that's using about 10 milliamps, but at a very low voltage. So the actual amount of power coming from LEDs is small. And what we do is, if we're looking at that energy, we'd also need to think about what's going to happen with it, because it might be light inside the panel, but that light's going to be absorbed by the panel itself and re-emitted as heat. But generally you don't need to worry about light, because the amount of light emitted is so small, it's dwarfed by your other power consumption. Now there may be additional calculations you need to do. Heat dissipation can build up in a panel. Heat can build up over time, and that might require more heat dissipation. And also you might need to consider in a panel what are external heat sources. So you assume that a panel is able to radiate heat outwards, but if it's in sunlight, it might even be absorbing heat, and that might also cause the panel to heat up. So there may be additional considerations. But generally, heat dissipation, you calculate the power consumption, and that gives you your heat dissipation in watts as well. Let's talk about earth and ground connections. In AC systems, the reason for having an earth or ground connection is as a safety protection. So in case there's any fault, like a loose wire or possibly a shorted component, what would happen is the current would flow from the live supply directly into the earth. That would bypass going through any human or any person, and what would happen then is the voltage and the current would flow directly into the ground, and it would be safely dissipated. Now that might trip a fuse. Alternatively, you might have a residual current device or some sort of electronic protection device, and that would detect that current flow, and often it would trip to prevent any dangerous currents. RCDs are very common in consumer circuits. And they're used for exactly that purpose. For example, if you had a washing machine and there was a short inside the washing machine, the short would go to the outside of the washing machine, which would make the entire cabinet live, assuming it's a metal cabinet. That would be very dangerous for the user, because if they touched it, especially with wet hands, then they could get a very dangerous electric shock and cause injury or even death. So the RCD would operate within a few milliseconds to trip the circuit and turn off the voltage. Now, we don't often see RCDs in industrial applications. One of the reasons is that a lot of electromechanical type devices like motors and something, they do have internal earth leakage currents. So if we use an RCD, what could happen is we could end up tripping the system accidentally when we don't want to. So we often see RCDs in consumer circuits, but they may not always be present in industrial applications. And the other sort of side of that is, the amount of current we need to short down as well. An RCD might need to trip a very large amount of current, so it would need to be a very big, expensive device. So we may have those as large protection relays, or we may not, but certainly RCDs are common in these consumer circuits. Now, in DC systems, you might also have an earth or ground connection. So there may also be a safety implication, although the risk of electric shock from anything below about 40 volts is low, unless you've got very wet skin. But also we might want that earth or ground connection as a connection point for shield wiring to prevent noise. So particularly for analog inputs, what you might want to do is you might want to earth for analog shield, and then the way that works is the shield receives all the noise, and then all that noise goes straight down to ground or earth without affecting the internal wires which are being used to carry your analog signal. Not required so much to 4 to 20 milliamp loops, because typically with 4 to 20 milliamps you use a pair of a single twisted wire, 2 wires, and then any noise received by one wire is also received by the other wire, and it cancels out. But for DC circuits, if you want to protect against noise, it's very common to use a shield. Also for thermocouples and RTDs, they may well need shielding as well. So that earth or ground connection can be used to prevent noise or to dissipate noise, as well as for safety. Now, it is important, particularly in industrial systems, to avoid earth or ground loops. You should only make the earth or ground connection at one point. Otherwise, you can actually end up with two earths which may be at different potentials, and then you can get a current flow between them, which can cause its own problems. So for example, that may overcome some electronic devices. I've seen two panels side by side which weren't correctly earthed, and there was a potential difference of 100 volts between them. So one, that was dangerous. It was strong enough that you could feel it electrically. You could certainly measure it using a multimeter. And that 100 volts might be high enough to overcome a 24 volt or an analog circuit and cause damage to that circuit. So you need to make sure that those devices are connected, but it needs to be a central connection only. Often you provide that connection via like one big terminal, and then there's a star connection, and you wire everything to that one terminal through that sort of star arrangement. Now, sometimes the downside of having wired to that single star is because there's lots of current going through it, hopefully not too much because that would indicate faults elsewhere, but there might be enough current going through it that there's actually noise on the earth signal itself. So what you might also find is you might have an earth or ground connection for safety, and then you'll wire a separate earth or ground to that via a single cable, and then have a separate bus bar or a separate earth connection. And what that does is it isolates the safety earth from the signal ground, and that protects you against some noise going back into circuits. So again, very important for analog circuits, particularly if you're concerned about accuracy of the signal, but also very important for safety as well. So make sure you've got a good earth ground connection, and there's various constraints about how that should work, and I think I've got a slide on that coming up. So here's some more detail of these earth or grounds and the sorts of issues you might face. So something you need to be aware of, sometimes the earth or ground is wired via a capacitor. The idea is a capacitor allows a AC signal to be sent, so that eliminates AC noise, but if you've got that capacitance there, it doesn't eliminate DC noise. So if you've got some DC circuits, if it's below 40 volts, again, that might not be a problem, although there might be enough voltage there to actually overcome the resistance of some circuits and cause damage to the circuits. But as soon as you've got a high voltage, if it can also flow at high current, then that could be dangerous to the operators. So check to see how the earth or ground is wired. So capacitance is bad. What you really want is a solid DC connection. Now it's also possible for the connection to the earth or ground to be too long, typically because the cable is too long. We think of cables as having no resistance, but they're made from copper or other components, other metals, and they do have resistance, and you can also get resistance at the terminations themselves. So what you should make sure is that the resistance in cables should be low enough to prevent the formation of any sort of voltage. Ideally it's less than 1 ohm, and you also want to make sure that the cable is thick enough with a large cross-sectional area, and that will minimize the amount of resistance, and that will reduce the voltage. So typically, quite a large cross-sectional area, 2.5 millimeters squared or higher, and you need to make sure that the terminations are secure and they don't have their own resistance. If the connection to the earth or ground is not secure enough, for example, you might have a connection to a DIN rail that's not intended to be used for earth or ground. That can be because, again, the resistance to the earth connection is too high and allow a voltage to be present. So you need to make sure, again, that resistance to earth should be very low, using a specific thickness of cable, minimum 2.5 millimeters squared cross-sectional area. And again, make sure all the connections are tightened. Another option there is also to use like star washers. Star washers are special types of washers that have connections on them that can actually make sure that you've got a better electrical circuit. Just connecting a wire to a DIN rail might not be enough to actually ground that DIN rail. You might get enough of a termination resistance there that you could still get higher voltages. So use of a star washer could give you some help there to make sure that that current is lower. But remember that DIN rail isn't necessarily intended to be used for earth or ground, so you might need separate earth and ground connections anyway going from your devices. Finally, you need to make sure about multiple earth and ground connections and daisy chaining. Again, that can allow a build-up of voltage. If you've got one earth in one panel going to another earth in another panel, goes to another earth in another panel, then that can ultimately end up in a higher than 1 ohm resistance, and also if you've got your cable resistance as well, that can build up to a high voltage. So ideally your earth or ground should be located at a single central point, and all your earth or ground connections should be made directly to that. You shouldn't be doing daisy chaining, and you need to make sure also that that earth or ground connection is near enough as well. Otherwise you may need specific additional earth or ground connections. And interestingly, we talk about earth or ground. People say, well, what is the earth or ground? It is literally a connection into the earth or ground. So I've seen this where if the connection to the ground is poor because it's a longer distance away, one of the things you might do is buy a large physical metal spike and you bang it into the ground. And this is, it's quite a large spike, maybe a meter long, but you hit it into the ground, and that gives your earth connection back into the earth, so your earth acts as your safety conductor. So that's another way of doing it, is actually provide a new earth or ground connection, and then provide your local safety signals into that physical earth or ground protection. So that covers the major aspects. I've got a few additional things which may be of interest, so let's go through some backup slides and they'll just give you a bit more background on what we've discussed. But if you just wanted an introduction to power supplies and power supply connections, then you can stop the video now and you're done. Let's cover industrial voltages. Industrial voltages are generally a lot higher than we see in consumer circuits, and they can be, as a result, a lot more dangerous. So we often see three-phase AC. AC is alternating current, where because of the way the voltage is generated, it's going up and down or backwards and forwards if you consider electron flow. But often the incoming voltages are extremely high, and we use transformers to bring those down into voltages which are manageable, but they're still dangerous. So for example, we might see a three-phase input coming into, say, a VFD or a control panel. It might be 380 volts or 415 volts AC. That's a very high voltage. We can manage that voltage into a smaller voltages using transformers. And the reason we use these high voltages is the higher voltage gives us more power at a lower current. So the alternative is, if we have much lower voltages, we'd need much thicker cables, which would be more difficult to install, more difficult to manage, and of course more copper, so it would be more expensive. But you often see three-phase for motors, particularly for large AC motors. 415 volt AC is quite common, but it's very dangerous. You don't want to touch that, definitely not. That's a high enough voltage to easily overcome the resistance of skin and cause a potentially fatal electric shock. Now, besides three-phase, we often see single-phase. The European standard voltage is 230 or 240 volts AC. 240 volts is common in the UK. 230 volts is common in Europe. The European standard is actually 230 volts with a wide range. So although it might be rated as 230 volts, it might actually be measured at 240 volts. That's common in the UK, where the actual standard is 230 volts, but the mains voltage is still coming in at 240. Anyway, single phase, so smaller current, but still dangerous. 230, 240 volts can cause an electric shock that can cause injury and death. So best avoided inside an industrial panel, but still required, because again we need that combination of high enough power and to reduce the amount of copper we need. Now in the US, it's common to see single phase 110, 115 volt AC. That's also common, or used to be common, in industrial circuits. But even the 110 volts is quite high and dangerous and cause an electric shock. Maybe it's not quite fatal, but it can still cause burns, and it can certainly be very startling to get that level of shock. So any sort of high level of AC voltage is normally avoided in modern circuits. So that brings us down to DC circuits, where it's a direct current. So we don't get the alternating current now. What we do is we convert via the industrial power supply, which we've covered. That effectively chops up the AC voltage and converts it into a static DC voltage using a switch mode arrangement. In modern power supplies, we use switch modes. In older power supplies, we might have used a transformer with a bridge and capacitors, but modern power supplies do that via electronic switching technology. So DC, 48 volts used to be quite common. I used to see it a lot in transportation applications and marine applications. 48 volts DC, although it's not that high, it can still cause an electric shock. That's high enough that can overcome your skin resistance, and it may not be fatal, but you can still certainly feel it. So these days we've reduced the standard voltage to 24 volts. As I say, that's the standard under the machinery directive. And now what you'll find is, unless you've got very wet skin, generally your skin resistance is high enough, you wouldn't feel a shock from 24 volt DC. Because it's as lower voltage, we do need thicker conductors though. So some occasions, some applications, you still have 110 volt or higher voltages, because otherwise if we had a 24 volt connection, the thickness of the cable would just have to be too thick and too expensive. Now we do use some lower voltages. 5 volts is used commonly for electronic applications, maybe also used for connecting encoders for motor feedback. Much lower voltage, effectively no risk of electric shock, but 5 volts can't carry much current normally, so it's only used for low current electronic applications. And then we also find 3.3 volts inside some electronic devices, but very rarely found in the outside world. The problem is, as the voltage goes down, the applicability of external noise can cause EMC effects, which can cause noise and interference. So, even down at 5 volts, that's an issue. Simple noise can easily affect a 5-volt encoder. So modern encoders are normally 24 volts. And when you're getting down to 3.3 volts, that's a much lower voltage. So on the plus side, no risk of electric shock, but could be potentially not noise immune. And again, if for large currents, you've got that additional conductor size you'd need. Now, we covered some brief calculations earlier. We were talking about power versus watts and current. So there are some standard calculations we use for AC and DC type power calculations. The first one that's very common is Ohm's law. So Ohm's law relates current and resistance to voltage. So the actual pure formula is volts equals current times resistance, or V equals IR. And we can rearrange that if we needed to, so we can calculate current. So if you want to know the current is, you can divide resistance divided by volts, that gives you the current. And you can also determine resistance as well by dividing volts by current. So if you know what the resistance is, for example, of a piece of wire, and if you know what current's going through it, you can calculate the voltage. And vice versa, if you know what the voltage is and you know what the resistance is, you can calculate the current and so on. And if you know the voltage and the current in terms of a volt drop, then again you can calculate there what the resistance is. So very useful for resistance type calculations. Not so often used in power supply calculations though. What's probably more common is that we would do these power calculations. So power is calculated as watts is the unit, and we calculate that as volts times current. So if we know what the volts is and we know what the current is, we can calculate power. If we know what the power and the current is, we can calculate volts by rearranging the circuit. And if we know what the power and the volts is, we can calculate current as well, again, by rearranging. So quite simple to get from any one of those. If we know 2 of them, we can calculate the 3rd one. One that's less likely to come up with power supplies is peak voltage. Peak voltage in AC systems, we take the RMS voltage, or the root mean square voltage, and you multiply that by 1.414. So for example, in a 240 volt system, if you measure the system, you'd see 240 volts using the multimeter, but the actual maximum voltage is 1.414 times the RMS voltage. Not particularly of use because you don't really worry what the peak voltage is, but I do recall it coming up in the past when I was specifying particular overprotection voltages or devices. So what I had was an AC system with 240 volts, and I wanted to put over voltage protection on that, so I needed to multiply the AC voltage by 1.414 to work out the actual peak voltage in order to calculate how much voltage my over voltage protection device needs. In DC systems, we don't really have a peak voltage. The voltage is the voltage, but there might be a small amount of ripple in the DC system. So again, you might still get a small RMS component, but it would depend how much ripple you've got. Normally we discount that, and a good high quality modern power supply, the ripple will be very, very small and negligible in practical terms. But occasionally you might want to use the RMS calculation if there's quite a high degree of ripple to understand what your nominal DC voltage is. But again, peak voltage, not really of interest. I think on this slide it's normally the power and the other calculations were there which are most important. Now, power supplies have a limited current output. We mentioned, for example, a typical power supply might be 5 amps or 10 amps. That's the nominal output power they can provide. Some power supplies might have their own current protection built in. They might also have over voltage protection as well, but that's a separate subject. But typically what happens is in your branch of your power distribution, you probably want to reduce the amount of power that's going to go through any particular branch. And to do that, we use fuses or miniature circuit breakers. So for example, you might have 10 amps coming out of a power supply, but what you might want to do is protect an input module which may have a rating of 1 amp. So you might use a 1 amp fuse or MCB to that particular input module. Now, what we do with overload protection is then, based on what the rating of the overload is, based on current, we normally size the overload protection to match that maximum current expected. So if we know there's a maximum 10 amp load, we would choose a 10 amp fuse or a 10 amp molded circuit case breaker, MCCB, or miniature circuit breaker, MCB, depending on your terminology. Now what you might need to look at is, the maximum 10 amp load, that might be a sustained 10 amps, but there might be a possibility of a inrush when you first start up. So that 10 amp load might be 15 amps for a few milliseconds when you first enable that load. So you can have overload protection which operates at different speeds. So if you're likely to see quite a long sustained overload when you first turn the system on, you might use a slow protection device. More likely you're probably going to use medium for most circuits. On the other hand, it might be that you really need to protect against anything above 10 amp, so you might want fast or even super fast overload protection. Just be careful of what the inrush is, because if you fit fast or super fast, then you might be overloading and tripping the fuse or the circuit breaker every time you turn the system on. So you can measure that using a multimeter. The problem is multimeters aren't very fast themselves, so you might need to even use an oscilloscope to work out what the actual incoming inrush is. If you're not sure, you can typically calculate that inrush as something like 1.5 times your maximum current for just a few milliseconds. And again, the vendor's documentation may give you more information there by telling you what the expected inrush is. So we talked about branch fusing. Most applications do require multiple current overload protection devices. So you'll typically have a master fuse on the main power supply. Then you'll have individual power supply fuses to each power supply if you've got more than one. And then you'll have branch I/O fusing that can protect each individual component or I/O modules. And it's possible, depending on how much fault tolerance you've got, but of course it costs more because the more fuses or MCBs you have, the more money you've got to pay, and also the more wiring there is to do, and also potentially you need a bigger panel. But you could go down to individually limiting each I/O point. It's more expensive, but it does aid fault finding and fault tolerance. As an alternative to that, on some particular output modules, you can get output modules with electronic short circuit protection, which might be better than individually protecting each output. But you've got to be careful there, because an ESCP module, some of them they reset when you just turn current off to that individual output. Some of them need the whole module to be power cycled. So again, you can refer to device documentation and look at what the current overload protection requirements are. And it's also based on what do you need for your particular application requirements, and also how much money are you willing to spend. So we talked about current overload protection. You can also get voltage overload protection. Some electronic devices are very sensitive to high voltages, so voltage overload protection is built into some power supplies, and the idea is this stops the voltage from getting too high. So if you look at a typical PLC, it's probably nominal 24 volt DC, but with a maximum of 30 volts. So you need to be careful that your voltage from your power supply doesn't exceed 30 volts. So what some power supplies have is built-in voltage overload protection using an MOV type device. It may be that's not wired in as standard. You may need to connect that via a jumper. It may be something that's not supported in floating neutral systems, so again, check for vendor documentation. But the idea of that voltage overload protection is if the voltage goes higher than the maximum specified, so for example for a PLC that might be 30 volts, what the MOV does is effectively either turns off the output, so that's often called crowbar protection. It can either turn off the output just by going open circuit, or some devices go short circuit, and that would trip a fuse or MCB as well. So there's a variety of different protection options there. If you think you need that, again, check your documentation for your power supply, or look at providing a power supply that can provide that. And it's also possible to buy external voltage overload protection devices as well. If you've got particularly sensitive or expensive electronics, you might want to have a separate protection device specifically for voltage overload protection.